here we talk about the potential energy, electric potential energy due to the charged particles. So here assume this one is the simplest case. We have two charges here. So within this system, there will be some energy stored in this system because, for example, this one we have two positive charges. Then you can assume that there will be a Coulomb's force repelling them. There will be Coulomb's force, K times Q1, Q2 over R squared. And then as much as you need to hold these two charges with a distance out, then you need to do some work so that they can keep the distance, keep with a finite distance. So actually, the energy stored in this system is like this expression: K times Q1, Q2 over R only. And yeah. And if there is a system with more than two charges, then the total potential energy of the system of particle is sum of the potential energy for every pair of particle in the system. So the expression look like this. This is U, the total potential energy, equals K times this summation. Looks horrible, but actually not so horrible, I think. So here is a summation, Qi Qj over Rij. Qi means the the charge amount of the ith particle, and Rij means the distance between Qi and Qj. So within this summation, we have totally n choose 2, or we can say it is NC2 terms, which is like suppose we have three particles, 1, 2, 3, 1, 2, 3, Ij. So here we cannot have I equals J, so we don't have this one, we don't have this one, we don't have this one. And U12 and U21 is actually the same. So this one is U21, U12. So we only count one of them. So here maybe we just pick this triangle. This is our U13, U23, U31, U32. So maybe we just pick this one, U12, U13, U23. So actually this is like there are three items. We pick two of them, and the total combination is NC2. NC2 is NC2. Sorry. NC2, or sometimes the book will note it like this, which is n factorial over 2 factorial times n minus 2 factorial. So for this case, n is 3, so we have a 3 factorial over 2 factorial times 1 factorial, which is 6 over 2 times 1, which is 3. So we altogether have 3 terms here. So this one will look like something like U equals K times Q1, Q2, and then over R12 plus Q1, Q3 over R13 plus Q2, Q3, and over R23, something like this. So if there are 4 terms, then if there are 4 particles, then we will have four choose 2 terms with n equals 4. If n equals 4, there will be 4 factorial over 2 factorial over 2 factorial. 4 factorial is 24 over 4 is 6. We will have 6 terms. So yeah, something like this. Okay, so here is an example. So as shown in this figure, 3-point charges held in a fixed position by the force that are not shown. What is the electric potential U of this system? So assume that D equals 12 centimeters. Q1 equals Q, Q2 equals minus 4Q, Q3 is plus 2Q, Q equals 150 nanocoulomb. Okay. So in this case, U, the total electric potential energy, is U12 plus U23 plus U31, or yeah. So it is like K times Q1, Q2, Q1, Q2. So actually this is a equilateral triangle. So DDD for the 3 sides. So over D plus Q2, Q3 over D plus Q3, Q1 over D. Yeah, like this. So we will have K over D, and then Q1 plus Q1, Q2 plus Q2, Q3 plus Q3, Q1. Okay, so then we can substitute the number. K is 8.99 times 10 to the 9th power over D is 12 centimeter, 0.12 meter, times here we have 1 times minus 4 plus minus 4 times 2 plus 2 times 1, and then times 150 times 10 to the minus 9th power quantity square, because Q1, Q2 we will have 2 factor of this one, so we have a square here. So altogether it is negative 1.7 times 10 to minus 2 power joule. Okay, so this is the potential energy stored in this system. Okay, so we have another one. This one, it says an alpha particle. This is alpha particle. It contains 2 proton, 2 neuron, 2 proton, 2 neurons, 2 neutrons, 2 neutrons. Move into a stationary gold atom. So this is gold atom with 79 protons and 118 neutrons. So which is much heavier. So passing through the electron region that surround the gold nucleus like a shell and headed directly towards the nucleus. Okay, so the alpha particle slows until momentarily stop when its center is radical distance. R equals 9.23 femtometer from the nuclear center. Then it moves that along its incoming path. Because the gold nucleus is much more massive than the alpha particle, we can assume the gold nucleus does not move. What does the kinetic energy Ki of the alpha particle when it is initially far away? So it's somehow like the classic mechanic problem. We will know the final potential energy as we know what is the closest point for the alpha particle and the gold nucleus. And at this moment, it is momentarily stops, which means that the kinetic energy at that moment is perfectly zero. So we can apply the conservation of energy to solve this problem. Okay, so we have a conservation of energy, the kinetic energy, and the potential energy is the total mechanical energy, and assume there is no loss here. So this is the initial mechanical energy and the final mechanical energy. Okay. So here we know. So when it is infinitely far away, the potential energy will be 0. So we know this one is 0, and also the final kinetic energy. This is the final point. This is the I at infinitely far away. So the final point Kf is 0. So we will quickly have Ki equals Uf. So Uf is nothing but K times Q1, Q2 over this R. Okay, so K is 8.99 times 10 to the 9th power, and then for Q1 is 2 proton, 2 times 79, and then it is a proton, so the elementary charge is 1.6 times 10 to the minus 19 quantity squared over R is 9.23 times 10 to the minus 15. Okay, so this one is 3.94 times 10 to minus 12 joule. So actually, this is the SI unit for the energy, and for particle physics, they usually use another SI unit known as the EV. So by transferring this value from joule to EV, we do this by 3.94 times 10 to minus 12 over 1.6 times 10 to minus 19. This value will be 24.6 times 10 to the 6th power times 10 to the 6th power EV. So this is EV, and sometimes we just write it as a 24.6 mega EV. They like this value because for a particle, for the energy of a particle, this value is very small, something times 10 to minus 12 power, which is a small number. They like to make it like larger than 1. So this is like 24.6 mega. So for the EV, the physical meaning is like you accelerate a particle with or you accelerate an electron with 1 volt potential difference. Then from no energy, then the kinetic energy will be 1 eV, something like that. So here we introduce the EV as the unit of the energy of a particle. Okay. So far, any questions? Okay. So here we talk about the potential of a charge isolated conductor. So this figure shows a car, and then this guy is inside the car, and then this is lightning shooting on the car, but this guy is fine. Because because the shell is just like a conductor shell. It's just like a conductor shell. So inside the conductor shell, the electric field is zero. The electric field is zero, so that there will be no current going through this guy. So this guy is safe. So, and it also in this page, it also tells you that suppose you know the potential, you know the electric potential, you can get the electric field by taking the derivative and then multiply by -1, you get the electric field. Or inversely, you can have the electric field first, and then you integrate it. You take the line integral, and then take the negative sign, and then you can know the potential difference. Just like here, usually for infinitely far away, we define the electric potential to be a zero, but yeah, may not be the case here. But this is just a reference voltage, which is not so important. But here we know that if we have the electric potential here, we take the derivative. So here this segment is flat, it's a flat line, the slope is zero. So if we take the derivative here, this is zero. So we have the electric field to be zero at this segment. And here, this one is decreasing. And as we know, V will be proportional to inversely proportional to 1 over R. If we take the derivative of this one, it will become a negative 1 over R squared. If we take the derivative, dr 1 over R, it will become negative 1 over R squared, something like this. So if we have another negative sign, it becomes 1 over R squared, something like this. Or if you integrate, so this one, E is proportional to, inversely proportional to R squared, something like this. Or if you integrate this one, the order will add 1 to this, will add 1 order to this term, so it becomes 1 over R, become this one. So we can have this one first to get the potential. You can get the potential first to get the electric field, or you can get the electric field first to get the electric potential. Both direction is okay. So up till now, from chapter 21 to chapter 24, we have learned several variables. We have learned the Coulomb's force in chapter 21, and then we learned electric field in chapter 22, and then V and U in this chapter. So actually, they are quite similar. The expression are quite similar if you consider two charged particles. And so here I just summarize the relationship between them. So for the chapter 21, we know the Coulomb's force or the electrostatic force. So we have a Q times Q0 over R squared. So it is like square for the numerator and square for the denominator. And the electric field, we only have Q. We only have first order of Q in the numerator and R squared in the denominator. And the relationship between the forces and the electric field is like this: F equals Q0E. For the potential energy and the electric potential, we have V equals K times Q over R, and the potential energy is like a Q0 over R. And the relationship between them is also similar. So we have F equals Q0E. Here we have a U equals Q0V. So this is the potential, this is the potential energy. So for these two, we have R squared in the denominator. We have R in the denominator for the potential and electric and the potential energy. So when we consider vertically, this is the force, this is the potential. So in mechanics, you should know that if you would like to know the potential energy or the work, you integrate the force over the path like this. So, or the other way around, you can take the derivative of the potential, you will get the forces. Similarly, for this one, between the electric field and the electric potential, we can take the derivative and then with a minus sign, and then we can get the electric field, or the vice versa. So we can have the electric field first and then do the line integral and then take the minus sign, we can get the electric potential. So this is a brief summary for the variable we learned so far. Okay, so here we have one or two additional example. So here, this one is simple. Here it says a plastic wad has been bent into a circle, like this one with a yellow one and a green one, bent into a circle of radius capital R. It has a charge Q1 uniformly distributed along 1/4 of its circumference, and a charge Q2 uniformly distributed along at the rest of the circumference. So this is a quarter of the circumference, which means the Q1 is here, and then Q2 is here. Okay, so with V equals 0 at infinity, what is the electric potential at the center of the circle? At the center of the circle. Okay, so yeah. Okay, so this question is pretty easy, because this Q1 charge is distributed along this circle, and as much as you would try to separate into many small segments, this is dq, and then you would need to find the potential at point C. So you will be able to find dV will be k times dq over r, and you just try to integrate from here to there for this Q1. And actually, the distance from the center to the circle is a constant. So this r is just a constant. So if we just do the integration, V equals integration of the dV equals integration of a k dq over r. This r is nothing but a constant, so it turns out to be k over r integration of dq, which is the total q, k over r times q1 for this segment. So this is very trivial. So the total voltage or the total electric potential will be like k over r times q1 plus q2. So nothing special, because all the charge are distributed on the ring, on this circle. Q1 is distributed here, Q2 is distributed here. It also tells you that the charge is uniform distributed, but even without the condition of a uniform distributed charge, then the answer will be actually the same. So here it is nothing but 8.99 times 10 to the 9th power over R. This should be capital R. Capital R here. Capital R. Capital R is 8.2 centimeter, 0.082 meter. And then Q1 is 1.2, or maybe we can have Q1, Q2 is negative 6. So we have 1 minus 6 times 1.2 times 10 to minus 12 power. Pico is 10 to the minus 12. So we have this expression. And the answer will be minus 2.3 volts. Any questions? Okay, let's have another question. Question B. The front part are actually the same. So here it just asks you the potential at point P here. The point P here. So yeah. So which is actually this is the axis. This is the axis for this circle, and yeah. So now if you consider dq here, and this is the distance from the circle to the point we concern, for the point P we concern. So this r is nothing but square root of d square plus r square according to the Pythagorean theorem. This is capital D, this is capital R. So no matter for every point, this is a right angle triangle because this axis is perpendicular to this plane. So if you consider dq prime here, this distance r prime is actually the same, equals d square plus r square. So even though the point we concern is not actually at the center, but as long as it is on the axis of this circle, then it is still very easy. So we can have r equals to square root of d square plus r square, which is 8.2 square plus d is here 6.71 square, and then take the square root of the whole term, which is 10.6 centimeter. 10.6 centimeter. Okay. So sometimes, usually I will convert the numbers to meters if I see the number in centimeter. But here we have two length in centimeters, and then take the square and then square root. So I just need to remember that this is still a number in centimeters, then it will be okay. If you feel worried, then you can just change it to 0.082 square plus 0.0671, and then the answer will be in meters. Okay, so here maybe we can say Vp is still K over R, and then Q1 plus Q2 still the same. The only difference is the distance. So we have 8.99 times 10 to the 9th power over 0.106, and then times 1 minus 6 times 1.2 times 10 to minus 12 power. Okay, so this one is negative 1.78 volt, which is slightly larger, or slightly smaller for the absolute value. This is minus 2.3. This is minus 1.78, because you can simply imagine that this point is farther from the circle than point C. So the inference for this ring to point P is smaller. Okay, so here is the third one. So here it says a plastic disc of radius r equals 64 centimeter is charged on one side with a uniform surface charge density sigma equals 7.73 femtocoulomb per meter squared. Then 3 quadrants of the disc are removed. So originally we have the whole disc, and then we put the charge density there, and then we remove the 3 quadrants. With V equals 0 at infinity, what is the potential due to the remaining quadrant at point P, which is on the axis of the original disc at distance d from the original center? So before we have already derived this expression for the whole disc. We have derived it for the whole disc. And now, because we only have one quadrant of the whole disk, we just multiply it by 1/4, because when we consider the potential here, actually we need to consider the whole disk. If we don't consider this 1/4 factor here to consider the whole disk, and actually you can find the symmetric property here. For example, you should imagine that this part should contribute the potential at point P, which is actually equal to this part, and also it will be equal to this part and also this part. So these 4 parts should contribute the same electric potential at point P. For example, if you consider this point, this part, you can find the corresponding position with the same distance from here to there. And here for this part, you can always find the corresponding parts which contribute the same amount of potential at point P. So here, if we only consider a quadrant of the disk, it just contribute 1/4 of the potential from a whole disk. So this is it, and then we can just substitute the number into this expression. So which is 1/4 times 7.73 times 10 to minus 15, which is this sigma, and then over 2 times of epsilon naught, 8.85 times 10 to minus 12 times here we have a square root. So we should be careful that this z here should be d. Z should be d. Z should be d here. And then this r, this capital R is still this capital R. So we should have this one 0.259 square, and then plus the R is 0.64 square, like this, and then minus D 0.259 like this. So the value is 4.71 times 10 to the minus 5th power V, like this. Okay, so I think that